Afternoon physics fans, it's a lovely sunny day here in London, so I figured what could be better than a question about gravitational fields from the AQA syllabus. So I picked the year 2020, paper 2, question 2. And it's your bog standard kind of question here. We have a planet of mass m being orbited by a moon of mass small m. We know that there's a period t for the moon to go around the planet once. And we're told that if we square that, we get some constant times the radius cubed. And we've been asked to find out what is the value of that constant. So we know that this moon is going to be going in a circular orbit, it tells us that. So we can therefore assume that the centripetal force on that object, or that moon, is going to be mv squared over r, which is going to be equal to the gravitational attraction between the two masses, which is this. So now we can do some algebra. We get rid of those m's, get rid of that r, cross out that square. We're almost there. The next step in this proof is just to recall that, as always, speed or velocity is distance over time. So if we set that time to one rotation of the mass of the moon going around the star, we can therefore say that it's the period t, and the distance in period is just the circumference, 2 pi r. So now we can substitute that lot in for speed or velocity. So that gives us that 2 pi r over t all squared, because it's v squared, equals g m over r. So now a little bit of algebra. That gives us 4 pi squared r squared t squared equals g m over r. We can tidy up with respect to the r's first, so we'll get rid of this one, and this one becomes a cube, r cubed. So now we have that, we've rearranged this one to give us r cubed over t squared, and this is going to be the value of the constant now, which is going to be g m over 4 pi squared. And so that implies that k, going back to our original equation up here, k is t squared over r cubed, but I've worked out r cubed over t squared. So in other words, we just have to flip everything. So that tells us that the constant t squared over r cubed is 4 pi squared over gm. Now of course you could do a slightly different approach to this question, would just be to remember, of course, that centripetal force is not only mv squared over r, but it's also m omega squared r. And that will lead you to some very dark places. No, it won't. It will just lead you to the same answer. In this next part, we are asked to consider the system of Uranus and 2 of its moons, Miranda and Umbriel, and asked to find the radius, the orbital radius of Umbriel. Well, we know from previous work that this is true. The period squared is equal to constant times the radius cubed. So in other words, whatever we get for t squared over r cubed for Miranda will be the same as t squared over r cubed for Umbriel. So we can write that r cubed over t squared is also equal to a constant. Now it's not the same constant as that one, it's the inverse if you like, but nevertheless it's still a constant, so it doesn't matter, we can flip the fraction upside down. So let's deal with Miranda first. So we can write 1.29 times 10 to the 8, which is the radius of Miranda, so we cube it, divided by the period, which is 1.41 squared, is equal to the radius of Umbriel cubed. That's what we're trying to find, so let's put a little subscript in there, divided by its period, which is 4.14 squared. And now you can see the absolute joy of flipping the fraction over, or flipping the t squared over r cubed over, because it makes the algebra much easier. So now all we do is just take this up there. When you put all that into your calculator and check it, always check this stuff a couple of times, you get 2.65 times 10 to the 8 meters, Now, I say check it a couple of times because it takes me 2 or 3 goes to be convinced I've got the right answer for this stuff. For some reason, there's just so many problems with this calculation. It's so easy to type a square when you meant a cube or something silly like that. Next up, you've been asked to calculate the mass of Uranus, which is big M, from the formula from earlier on. So that means you need to rearrange it to get what M equals and then just bung in the numbers. So 4 pi squared r cubed over g equals mt squared. So that means 4 pi squared r cubed over g t squared equals m. Now, you've got to use one of the sets of data now to work out what the mass is. And of course, you're going to pick Miranda, aren't you? Because that's the data you were given, rather than using the value you got here, in case you got it wrong. So definitely use Miranda. And when, of course, you do that, you get 8.55 times 10 to the 25 kilograms. In 2.4, we've been asked to find out which of the 3 other moons of Uranus has a greatest escape velocity for an object on its surface, and it tells us to just ignore Uranus in this calculation. Well, this is a potential energy, kinetic energy question, so we know that the potential energy on the surface of the planet, technically it's minus, is going to be gm over r, and that's going to be turned into kinetic energy completely if it's going to escape, which we know is half mv squared. So this is worth pointing out straight away. This is for 1 kilogram because V, the potential, is per unit mass, or 1 kilogram. Therefore we can say gm over r equals a half v squared, and so the escape velocity squared is going to be 2gm over r, and so the escape velocity v is simply the square root of 2gm over r. You might be wondering why I just sort of disappeared the minus sign and moving from here. That's because we're looking at changes. How much the potential goes up has got to be provided by the kinetic as it goes down as it leaves. So we're okay just to look at the values and kind of forget the signs in this case. And now it's just a question of doing another column on the table. And because we have that V is 2g over m over r, 2 and g are obviously constants, so we can just say that the velocity is proportional to m over r, where m is the mass of the planet in question. So we just go through and work out the values for each of those. You know, I'm going to leave you to do that. When you do that, Titania comes out with the highest value. Question 2.5 asks us to consider a spring mechanism on Earth which is firing an object up to a height of 1 meter, and then taking the same spring and the same object, same mechanism, all of it, off to the surface of the moon Ariel and seeing if we can get higher than 100 meters. Well, we're not given any sort of mass here, but what we are told is it's the same object. So let's make it the unit mass object, or the test mass object. So we'll let m equal 1 kilogram. So the first thing then is to kind of work out if it's going up 1 meter on planet Earth, where we know that g is 9.8, how much energy then has it gained? In other words, how much energy is stored in the spring? Well, elastic potential energy, EPE, is going to be equal to mgh, which of course is 1 times 9.8 times 1, i.e. 9.8 joules. So we're now going to take our spring, which has got 9.8 joules stored in it, up to the surface of Ariel and see how high 1 kilogram can be fired up. So what we need then is to find the value of G, gravitational field strength, on the surface of Ariel. Well, that of course is equal to gm over r squared. So 6.67 times 10, times 10 to the minus 11 times the mass, 1.27 times 10 to the 21, over 1.16 times 10 to the 6, but don't forget that's a diameter and we need a radius, so divide that by 2 and square, and when you do that lot you get that G comes out as 0.25 newtons per kilogram. We know, of course, that our spring has that much energy in it, so we can say the elastic potential energy is 9.8 joules, and that's equal to m, the mass, which is 1 kilogram, times g, which for the Ariel is 0.25, times h. In other words, the height now that it will go on the surface of Ariel is just 9.8 divided by 0.25, which is going to come out as about 39 meters. So the answer to this question is no, it's not going to go over 100 meters. Hopefully you found that oh so marvelously useful.